What's up, everybody? In this video, we're going to be covering USACO's 2021 February contest at the silver level. Problem number 3, just green enough. Farmer John's pasture can be regarded as an n by n grid where n is between 1 and 500 of square cells of grass. Picture a huge chessboard. Okay, so we've got a big board like that, and then each one of these has grass on it. Due to soil variability, the grass in some cells is greener than in others. Each cell, ij, I guess where I would be the row and j would be the column, is described by an integer level of greenness, gij. So the greenness of ij, you can just think of that as a function. So the greenness of ij ranges from 1 to 200. Farmer John wants to take a photograph of a rectangular subgrid of his pasture. So basically he wants to take a picture of some part of the pasture that's not necessarily the entire pasture. He wants to be sure the subgrid looks sufficiently green, but not ridiculously green. So he decides to photograph a subgrid for which the minimum value of G is exactly 100. I'll read that again. So he's deciding to photograph a subgrid for which the minimum value of G is exactly 100. That threw a lot of people off. What that is exactly saying is that in that photo somewhere, there must be a 100 and nothing less than 100. So nothing less than or equal to 99. It has to have at least a single 100. It could have multiple 100s, but it has to have at least a 100 and nothing under 99. So if you had a rectangular subgrid, just to really hammer this in, that had like a 150 and a 130, that's 2 green. If you have a rectangular subgrid that has a 73 and a 100, that's got a 73, so that's not green enough. If you have a rectangular subgrid that has a 100 and a 110, then this is what you want to photograph. And it doesn't have to just be 1 by 2. It could be any size. But we must have a 100, and then everything in the field must be 100 or higher. Okay. And we have to have 100. So it can't be, again, it can't be 120, 130. That's no good. We must have at least 100. Please help him determine how many different photographs he could possibly take. A subgrid can be as large as the entire pasture or as small as a single grid cell. So it could be just exactly 1 by 1. There are n squared times n plus 1 quantity squared over 4 different subgrids in total. This is a huge red flag right here. This n squared times n minus 1 squared, that's basically n to the 4th. Since n is 500, we potentially have 500 to the 4th subgrids, which is, what is that? 25, 125, what is it then? 625, and then 1, 2, 3, 4, 5, 6, 7, 8. 62 billion, which is 6 times 10 to the 10th. That 10 to the 10th thing is your red flag. This goes over. So what that means, and this is just thinking out a little bit, we do not have the time to check every single subgrid. And that is what makes this problem very difficult. This actually is a very difficult problem for a lot of people. Because we cannot check every subgrid, we have to find ways to optimize that. You're going to have to optimize this using dynamic programming in 2 dimensions. So it's a little bit tricky. So buckle up. There's that many different subgrids in total. Note that this this number might be too large to store a standard 32-bit integer, so you might need to use a 64-bit integer data types like a long in C++. So that's another thing. Make sure you use a long, even if you have the right algorithm. Your number of subgrids might be too high. That's another big hint too. Your integer max is 2.1 billion roughly, which is 2 times 10 to the 9th. What that means is we can't count our subgrids 1 by 1 either. So even if we didn't have to look at every subgrid, if we're counting our subgrids just with +1, +1, +1, that alone is going to be over our time complexity. So even if we could somehow filter out only the grids that are valid, we still can't add them one at a time. We have to add them in blocks, and we're going to be using some kind of multiplication for that. There was a lonely photo. I don't remember. That might have even been a bronze problem. There was a lonely photo problem that you may want to do first if you haven't seen this. It involves having cows where you've got like Holsteins and Guernseys. So it'd be like Holstein, 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 Guernsey, Holstein, 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 Holstein. And this is, again, thinking kind of far ahead. But we have to figure out how many different photographs there are with one single Guernsey. You can't count them because you've got the Guernsey here and then Holstein, Guernsey, Guernsey, Holstein, all 3 of them, HHG, HGH, GHH, HHGH, there's a lot of them. But what you can do in this case is to know how many photos there are. You've got 3 starting points and 4 ending points. So you could just do 3 times 4. And that'll tell you how many there are that start here and start on the left side and end on the right side. Then from there, you just have to figure out how many start or end on the G. We'll come back to that, but this is a very similar operation. Essentially, what you're going to have to do in this past here is you're going to be figuring out a collection of like, this is all valid data, this is all valid data, with the G in this case would be like a 100, and then you're multiplying on either side to figure out how many there are. That's one of the two optimizations. The other is going to be prefix sums. We'll get to this, but yeah, that's called lonely. Let me double check if I can pull that up real quick here. Lonely. Might not have done a video for that one yet. Yeah, I haven't done a video for that one yet. I'll have to do that video next. But it's called, I believe it's called Lonely Cow Photo or Lonely Photo, something along those lines. Okay, so anyway, moving on, we have input format. The first line of the input contains n. The next n lines each contain n integers and collectively describe the greenness values for the n by n pasture. The output format is printed to terminal standard out. Please print the number of distinct photos Farmer John can take. That is the number of rectangular subgrids for which the minimum level of greenness is exactly 100. We've already explained that. Note that the large size integer, oh, I already read that, didn't I? Okay, sample input. So first is N3. That tells us that this is going to be a 3 by 3 grid. 1, 2, 1, 2. These are all the values, 57, 120, 87, 200, 100, 150, 2, 141, 135. Okay, and it says there are 8 subgrids. Let's see if we can find them real quick. So I'm going to switch colors here. Okay, so first thing I'm going to do is I'm going to look for 1 by 1s. Anything that's just a 100 by itself. So that's 100 right here. That is a single 1 by 1. So I'm going to say that there's one of them. And this is not how the algorithm works. I'm just doing this visually. Next is 1 by 2. So 1 row, 2 columns. So I've got the 200, 100 as a valid one, and I've got the 100, 150 as a valid one. So there are 2 of those. Next up, I'm going to have 2 by 1. 2 by 1 is going to include this 120, 100 here, stacked up vertically, as well as the 100, 141 underneath it. There's 2 of those. Then I'm going to go by 2 by 2s. 2 by 2s. The only 2 by 2 I have is this one right here, at the very bottom right. That's a 2 by 2. There's one of those. Next, I have 1 by 3s. 1 row, 3 columns. This entire middle row here, that's a 1 by 3. There's one of them. And last is 3 by 1s. That's going to be this whole middle column. 1. So those are the regions we're trying to identify. But remember, not only do we not have the complexity to check every subgrid, but even if we could filter out only valid subgrids, we can't count them 1 by 1. So we need a much more clever approach than this. To start off with, we will talk about the brute force approach, though. For the brute force approach, let me just clear this and rewrite it. For the brute force approach, let's even consider making this a little bit larger. I'm going to do 57, 120, 87, 103. I guess this one doesn't matter. And 112. We're going to do 200, 100, 150. Let's throw another 100 over here. And let's do like 88. Let's do 200, or let's follow what's on the grid just for this row, and then I'll add another row at the bottom. 2, 141, 135, 190, and 180. We need 2 more rows. Let's do 200. I'm gonna just make these easy. 200, 200, 200, 200, and then 200, 80, 200, 200, 200. Okay, so at the core of this problem, I'm going to switch to my blank screen too. At the core of this problem, what we're trying to do is we're trying to look at every single grid. So let's brute force it just to think about what that implies. What that means is we would essentially need a for loop that checks for every column and then for every column plus 1. So that would work its all the way across for that starting and that ending column. And then for the next one, so I goes up to here, and then J would run down, and then I would go up to here, and J would run down. We want to look at every potential starting and ending column. And again, we can't really do this with a nested for loop, but that's conceptually what we want. We want to consider every potential starting point, every potential ending point. For the rows, so we've got like I and J already. Now we need like a K and an L essentially to check every single potential starting row for K, and then for L starting at K plus 1 running all the way down, and then k would increment, and then L would run all the way down, and so forth. So for every single starting and ending row, for every single starting and ending column within that grid, we would need to check for every row. So now we're up to M and N. For every row and every column, we need to check to see whether or not we have anything that is under 100 and whether or not we have at least one 100. As long as we have at least one 100 and nothing under 100, like for example in this one, that's a valid grid. Now, not only is this search way over our time complexity, but again, even if that wasn't over our time complexity, the number of grids we're going to find is potentially more than what an integer can hold, which means if we do that all with +1 + 1, it's going to be over our time complexity. So we're going to need a handful of optimizations on this. The first optimization, if you have I to j, I'm going to write all this back. So, and this is actually not a bad way to approach these problems. Write out the brute force solution and think about what you can optimize. So if what I need to do, I'm going to make I to j to the edges. What's the widest grid I have here? I have one that goes like this, and then all the way over here. Let's actually change that 88 to a 188, so I can go all the way to the edge. I want to have a 4x3. Okay, so let's say like this is what I have to work with. Essentially, what I've got is I is over here as my starting column. I've got j over here as my ending column. I've got k on this one as my starting row, and L down here as my ending row. And then I'm going to have M running through my rows and N running through my columns. Now, in order to optimize this, the first thing that should jump out at you is prefix sum. If I need to know on this row whether or not there are any 100s and whether or not there are anything less than 100, I don't want to do that in linear time by working my way across with that. I want to get rid of that dimension. The way I can do that is with a prefix sum. Now, for this prefix sum, we're going to need two numbers. The first is going to be how many numbers are there that are less than 100? And the second is how many are less than or equal to 100? Now, the reason why I need to know this is because I need to know for sure that the number less than 100 is exactly equal to 0. And the number that is less than or equal to 100 is exactly equal to 0. Or, depending on what this number is, that this is offset. So the difference of those two. If, for example, the number that I have that are less than or equal to 100 is 1, but then the number that I have that is less than 100 is 0, then what that suggests to me is I have nothing under 100, but I have at least one thing that is less than or equal to 100, which means I have a 100. And you can use subtraction to find the two. If I have anything here at all, or actually I don't even need to subtract. If I have anything here at all, 1, for example, that means the whole thing's disqualified. If I have a 2 here, for example, then that means that I have two numbers that are 100 or less. But if I had like a 90 and a 100, then I would have at least 1 here. And as long as we ensure that this is a 0, this less than 100 is a 0, then that means that whatever we've got here are 100s. And it's just easier to do less than 100 and less than equal to 100 than to try and count how many are greater than 100. If you count, if you have how many are greater than equal to 100, then that doesn't. I guess you could do the same. It's probably inverse. It just feels like it's easier to work with less than. So prefix sum. I'm going to switch colors here. We're going to have the number of numbers that are less than 100 first of all. So starting with 0 of them, 0, and then after 200, still 0. After 100, still 0. After 150, still 0. After 100, still 0. After 188, still 0. Here I've got 0. After 2, I have one number that is less than 100. This is less than 100. After 141, still 1. After 135, still 1. After 190, still 1. And after 180, still 1. By the way, if you don't know how to prefix sum is or how to do one, I need to make a video on explaining this. It's a really, really common technique for figuring out how many times something occurs. If you're not familiar with prefix sums, you may want to take a break, and you can either Google it or hopefully by the time you see this video, I'll have posted an example on how to do prefix sums on the table of contents page. Okay, so 0, and then still 0, 0, 0, 0, and 0. So just briefly, then, what you can do is if you want to know how many numbers there are that are less than 100 within the range of I to j, you have the number after a particular value. So this is how many there are after j. And then this here is how many there were before I. And if it goes from 0 to 0, I didn't gain any, which means that there are no numbers in that range that are less than 100. Here I've got a 1, but that doesn't mean that there's one number less than 100. It means that as of this point after j, I had one number that was less than 100. This number right here is how many there were before I. So even though there is a number that is below 100, it went from 1 to 1 in the course of going from I to j, because this was not less than 100, this was not less than 100, so none of those incremented this counter. Because none of them incremented the counter, that lets me know that I don't have any 100s in that range, and then here to here, same story. So that's your first optimization. Your first optimization is using prefix sums to find instantly, essentially within a row, how many less than 100s there are and how many less than or equal to 100s. Let's do less than or equal to next. Less than or equal to 100. Okay, so here I've got 0. I'm going to write them right next to each other. 0. Now I've got 1. Here's 1. Here's 2. And then here's 2. Here I've got 0. Still 0. Still 0. Still 0. In fact, there's no 100s on that row, so it's going to be 0 all the way across. Here again, 0, 0, 0, 0, 0, and 0. So regarding this IJ box, what we've determined is that within this IJKL box here, if I want to know how many 100s I have, exactly 100, let's actually write these both down. So numbers less than 100. I've got here 0 minus 0, 1 minus 1, which is still 0, and then 0 minus 0, which means I have 0 numbers that are less than 100. For the numbers that are less than or equal to 100, I have 2 minus 0 here, which means I've got 2 of them. And then I have 0 minus 0, that kind of sloppy, and then 0 minus 0. So there are 2 numbers that are less than or equal to 100. Oh, you know what? I didn't count that right. Let me look at that again. This should have been a 1, sorry. And that's a 1. That's going to be a 1. That's going to be a 1. That's still a 1. So that still indicates no 100s, but this 2 should have counted as less than or equal to. Let's see here. We got that. Okay, yeah. So I have 2 numbers that are less than or equal to 100 because again, the 1 minus 1 would have canceled out. 2 minus 0 would have given us a 2. So I have 2 numbers less than or equal to 100, and I have 0 numbers less than 100, which means I have 2 100s in this range. So that is your first optimization. Your first optimization is using prefix sums to be able to sum across. Now, the next problem that we're going to run into, I'm going to go ahead and clean this off here. The next problem we're going to run into is we don't have the ability to look at all these subgrids. So what's going to happen with K and L is we're not going to make that part of our nested loop. We are going to have a nested loop. I think that was an 8. We're going to have a nested loop for I and j. So for I from 0 up to however big the thing is, and then for j from I plus 1 to whatever the thing is. But then that's determining a column. Let me write this out as a column. So let's say like we just ignore everything else and we say, okay, I want to try and do the fastest way to solve the I plus j subrange that I possibly can. Try that a little cleaner. Okay, so I want to solve this I plus j subrange, and I have my prefix sum numbers. I'm just going to kind of magic write the answer here. So in this row, the number of less than 100s is 1, because here I would have had 0 and then 1, and then let me actually just write this one out to make sure this is clear. I have 0, then after the 57, I have 1 number less than 100. After the 120, I still have 1. After the 87, I have 2. After the 103, I still have 2. After the 112, I still have 2. 0, still 0. That was supposed to be a 100. I erased that on accident. 100. 0, 0, 0, 0, 0, 1 from the 2, 1, 1, 1, 1, 0, 0, 0. These are all zeros. 0, 0, 0, 0, 0, 0, 0. For numbers that are less than or equal to 100, we have 0 here, and then 1, and then still 1, and then that becomes 2, and then still 2, and then still 2. This is 0, and then still 0. This now is 1. This is still 1. This is now 2, and this is 2. 0, 1 from the 2, because again, less than or equal to. 1, 1, still 1, still 1. And then this is all going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. So now that we've done this, we want to try and optimize solving this. Now, this is what I was talking about, the lonely cow photo part. What we're trying to do is we're trying to figure out within just this strip here of I to j, how do I calculate how many of these rectangles are valid? And so what I'm going to do is I'm going to send my first runner out to try and find a situation where a cow is less than 100. So here I've got 2 minus 1. That indicates a cow that's less than 100. So I'm going to stop my counter there. And then what I want to do then is find where do I have less than or equal to 100. And then I go here to here. That's going to stop there, and less than or equal to 100. Now, because I've got less than 100 and less than or equal to 100 on the same row here, that means that as of this point, I don't have any valid subgrids. So then this is going to continue down. Hang on. Yeah, because of the 87. Okay, so this continues down. So then the next time I find where I have less than or equal to 100 is going to be here, from here to here. And the next thing where I have less than 100, that's actually going to go to here. That's valid. To here, that's valid. To here, that's valid. And I can check these in constant time because I'm doing the end minus the beginning. It's going to make it all the way to the bottom. The bottom is, I made it all the way to the bottom. I didn't find anything less than 100. Now, what that means is that I found a 100 on this row right here. And I made it all the way to the bottom before I found something that was either to the end or less than 100. Now, this grid is not a single grid. This grid means I actually have 4 grids, because one of them is just this top by itself. One of them is this valid grid right here. One of them is this valid grid right here. One of them is this valid grid right here. So that's 4 grids. Let me give you I'm going to give a simpler one with less numbers, because then we don't have to count as much. So say like I have 1, and then 200, 200, 200, 200, 1, 1, 200, 200, 200, 200, 1, 1, 200, 100. That'll be the key part. 200, 200, 200. I had 6 of these. 1, 200, 200, 200, 200, 1. It's just ones here. 1, 200, 200, 200, 200, 1, 1, 200, 200, 200, 200, 1. Okay. So again, for I, and then J running all the way across, just focusing on this one column here though. At some point, we're going to have I here and J here. And this is your n squared aspect right here. So because n is 500, this is going to be 500 times 500, which is 25000. You have 25,000 columns that you need to check. That's a very reasonable number of columns. We do not have the ability to check every subgrid though, as I've stated, because if we were to then multiply that by 25,000 potential rows, then we've got that, what is that, 625, I think, 00000. It's too big. But we can check 25,000 subcolumns. So for this one single subcolumn in particular, this is one of the 25,000 potential subcolumns that we have right here from I to J. We want to find a fast way to count how many subgrids there are. Now we know that there's a 100 here. If we were to just eyeball this, then we've got the row that has just the 100. I'm going to go ahead and circle. We have the row that has just the 100. That's 1. And then we would have, for rows of size 2, 2 and 3. For rows of size 3, we would have 3, 4, and 5. That's rows of size 3 up to 5. Let me clean that up. 2. So up to rows of size 3, we have 5 grids. For rows of size 4, we would have this one right here. That's 4, 2, 3. So we have 3 rows of size 4 until we hit the bottom. Rows of size 5, 2, 3, 4, 5. We have 1, 2 of those. 5 results in 2, and 6 is 1. So the number of grids we have here is 5 plus 3 plus 2 plus 1, which is at 8, 9, 10, 11. I think I missed one. Let me look at that one more time. Did I get the 1 by 1 row? I have 1 of size 1. I have 2 of size 2. Oh, right, because one of them would go off the top. My size 4 row, I have a size 4 here with the 100 at the top, but I don't have a size 4 with the 100 at the bottom because it goes off the top. That's why I'm missing one. So I think 11 is right. So the way we're going to do this, looking at that number again, remember we were going to have these prefix sums. So on all of these sets, the number is going to be 1 to 1 for the number of, actually less than 100, I did in blue. Let's keep that consistent. For the number that were less than 100, I have zeros. I guess this is going to be 0, 1, and then 1, 1, 1, 1, 2. But we're not going to have any 100s within that range. So if you're using your prefix sum as you work your way down, since you can just subtract the last number minus the first number to find out how many less than 100s you have, and that would be a very quick way to check down. So you're looking to stop when you hit something that is less than 100. Let's just say for giggles, then down here I had like 1, 1, 1, 1, 1. So that's where that would stop. So you send your first runner out. It needs to have less than 100. And it's going to find that bottom row, and that's where it's going to stop. So your less than 100 is going to stop on this bottom row. And then you have one that is for less than or equal to 100. That's going to get stopped on this row right here. And then you have one more counter, which represents your top. I'm going to do that in black. The top is up here. Top equals 0. So from the top, I send my first runner out to find how many that I have that are less than or equal to 100, and it's going to stop on this row right here. I send my next one down to find strictly less than 100, and it stops at the bottom. So what that means is, if I look at this, if I were to consider each of these, I have 2 potential starting rows, and then I have 3 potential ending rows, and I have 1 in the middle here, which is where my 100 is located. Now, depending on how you want to write this algorithm, there's a lot of ways to write this. Essentially, what we've got is we've got 2 starting locations and 3 ending locations, which means that for rectangles that start above that row that has the 100 and rectangles that start below, we've got 2 times 3, which is 6, that are including above and below. In addition, we've got 3 where the 100 is on the bottom, and we've got 4 where the 100 is on the top. Sorry, 1, 2, 2 where it's on the top, 2 where it's on the bottom, 3 where it's on the top, and 1 where it's only that row by itself. So a couple ways you can count that. One of the ways that's pretty easy to count that is to move your top, whoops, that's not what I wanted to do. Move your top counter down, and every time you move your top counter down, however many ending points there are, count that towards your total. So when the top is here at the top, I've got 1, 2, 3 ending points, and I can find that by doing this. I can subtract that away from this. So if your bottom row is down here and your 100 is found on this row, you get the difference of those. You find that that's 3. And then as you count the top down, that's going to be plus 3. Because for this one as a starting, you can have, no, it should be to the 100. It should be 4. Sorry. For this top row as the starting, we can edit here 1, that's a subgrid, 2, 3, or 4. So because that's how many are valid underneath the 100 before we hit that row with the ones down at the bottom. So we've got plus 4 for that. We move our top counter down. Now our top counter's here. For here again, if this is the starting, we have 1, 2, 3, and 4. So that's another plus 4. We move that down. For this is the starting. For this is the starting, we have 1, 2, 3, and 4. Yeah, so it was 12. I did miss one on the earlier count. So that's representing this from here to the 100, to the 200, to 300, and to the 400. For this one, as a starting value, we have to the 100, to the 200, to 300, and 400. And for this one, with the 100 as a starting value, we have just that row by itself, and then here, here, and here. And those are our 12. Let me see if I can recount those again. Size 1, size 2, it's going to be 1, 2, 3, size 3, 4, 5, 6, size 4, 7, 8, 9, size 5, 10, 11, and then size 6 is 12. Yeah, okay. So there are 12 of them. So again, this is a pretty heavy problem. You will need to use prefix sums. Once you use the prefix sum, let me clean this up. Once you use the prefix sum, essentially what you're doing is for every single potential starting row, every potential starting column and every potential ending column, which again, there are 25,000 of them, you have an I and a J that are going to loop through every possible combination. And then for each of those, using those as endpoints, we need to work our way down the row. I'm just going to use color coding in general. Anything where you have a number less than 100, I'm going to do that in blue. So let's say like this is a row that has at least one number that is less than 100. You can determine that using the prefix sums. This is going to be one that has a 100, and then I'll do red for anything that has no specific 100s. So no specific 100s here, no hundreds, no less than 100, no 100, no less than 100. We'll have another row that has 100 in it, 100 in it, and then maybe no specific less than 100, and then finally blue on the bottom, we have something that has a number less than 100 here. So essentially what you're needing to do is you're needing to figure out, let me actually put a red between that green to just demonstrate that. Let me do these as squares actually. Okay, so I've got a row that has a 1 in it. I have a row where everything is above 100. I have a row where I've got at least a single 100 and nothing below. I've got a row where everything's above 100, maybe another one where everything's above 100. And here's another row with a 100 in it. Let's put one more where it's all above 100. And then at the very bottom, we'll have our final row has something that's too small. So what we're needing to do, again, to just kind of recap this, and you may want to try this on pencil paper, just think about this. But assuming we've got our IJ figured out, assuming that we've got a way to quickly find out how many things there are in a row as far as less than 100 or greater than 100. Anything where it's less than 100, I made it in blue, so less than 100. Anything where it's less than or equal to 100 is in green. And then everything else that is not red, blue, or green can be assumed where everything is greater than 100, greater than 100, greater than 100. So well, your runners are going to work. And again, there's different ways to do this. But you're going to send your first runner down to find something that is less than 100. That's a hard stopping point. And then you're going to have something that goes down to find anywhere that you've got less than or equal to 100. That's sort of a pivot point. And then you're going to have a top section. Your top section is going to find the first row where it's not blue, essentially, where it's not less than 100, which means greater than 100 is okay and less than 100 is okay. What this indicates is that we have the difference from here to here, from the very bottom row to that 100 we found. Those are all potential stopping points. So for this top row, we have from here to here. That's your first valid subgrid. Second one is top to here. Third one, fourth one, fifth one. For this top, we have 5 stopping grids. The way we can find that is the difference between this column here and this bottom column here. 1, 2, 3, 4, 5, and then 6 if you count it. Because I've got 6 potential stopping points. 1, 2, 3, 4, 5. Wait, 5 potential stopping points. Yeah, because there's a difference between the blue one. Let me number these real quick. 0, 1, 2, 3, 4, 5, 6, and 7. Yeah. So if my less than 100 is on 7 and my 100 is on 2, and I have 7 minus 2, which is equal to 5, means I have 5 potential stopping points, but this is my top. So that's going to be plus 5. Then the top is going to move its way down. Top reaches this green. And then for this being potentially the top, again, I have 5 potential stopping points. 1 here, 2, 3, 4, and then 5 right under that red. So it's another plus 5. It's the same 7 minus 2. Now, once the top goes past the green to here, my counter for the green part needs to work its way down to the next green one that's underneath the top. So your top is working its way down, and you've got 2 runners here, one looking for blue, one looking for green. Anytime either of them is less than top, it's got to find the next one. So this is going to find its way to this next one right here, and then that becomes your next pivot point essentially for green. So again, oops, let me rewrite that. With this top, you know, your potential stopping points have to be below green, because remember, you have to have a green one. So I don't have, for example, I don't have this. That's not a subgrid. I have to get at least down to the green. So again, your stopping points include this one right here and this one right here. There's 2 potential stopping points. So first subgrid is from here to here using 3 rows, because that will incorporate that 100 that we have on that green line. Second is going to be from here to here. That would include that red one. So I've got 2 subgrids with this as the top. So it would be plus 2. The top moves its way down. I have 2 from this standpoint. I have from here to here. That's a subgrid, including the 100 at the bottom. And then the next one down. That's a subgrid using the 3 rows together. So that's another +2. Top works its way down to the green one. Again, with the top here, we're still on valid territory because this is not less than 100. The green can be on the same spot. So again, I have 2 stopping points. I have with the green one here with this row as the top, I have that row to itself as well as to the one below, and that's another +2. So I've come up with 5 plus 5, this 5 over here, plus 5, plus 2, plus 2, plus 2, which is 10, 11, 12, 13, 14, 15, 16. I have 16 valid grids is what I've come up with. Now I've just done that in linear time. So what we're able to do is in n time, we are able to run through, because notice we didn't have to start over. Our top worked its way down. And yeah, we had 2 other runners. I had a runner looking for green and I had a runner looking for blue, but both of those only had to make 1 pass. Neither of them had to backtrack. So that was essentially 3n. I have 3 runners that had to make their way through. I have 3n times n squared. N squared times 3n, which is going to be 500 squared, which is 25,000 times 3 times 500. So 75,000 times 500 is going to be 75, 1, 2, 3, 4, 5 times 5, which is, what is that? 150, 300, 450, 1, 2, 3, 4, 5, 45 million. So we're still well within our time complexity. And the way we've done that is we've eliminated the need to check across the column. We've eliminated 1 dimension by using our prefix sum. We've eliminated our second dimension by working our way down, targeting greens and targeting blues, and then basically just counting them as we go, which is essentially the same as multiplication, because however many ending values we had, remember when we had the green one here and then the blue one here, we know the difference between those two was 5, I think is what we came, or that was on the last one. 1, 2, 3, 4. No, that's 5. Yeah, that's right. This problem. So we've got 5 here, and then I'm counting 5 for this, 5 for this, and then 5 for that. Or no, sorry, not for the top one. 5 for this one, 5 for this one. That was 10. That was where my first 10 came from. With this as a top, and then with this as a top, counting then this bottom, this bottom, this bottom, this bottom, this bottom. That's essentially 5 times 3, but we're counting them as we go. So plus 5 plus 5 plus 2 plus 2 plus 2, that is 16, I think I said. And then just to kind of eyeball this, make sure that we have our sanity check, our numbers that have a difference of, sorry, columns that have a size of 1 include this column right here, size of 1. This column right here is size of 1. Columns that has a size of 2, I have this one, this one, this one, and this one. Columns the size of 3 are this one, that one, that one, and that one. Size 4, that's going to be all of them again. 1, because then they're all incorporated, and then 5, 5, and then 6 is the whole thing. So there's a lot to do on this one, but your first optimization is to use your prefix sum to figure out how we can get for some column I and j with a starting and ending point. How can I figure out how many in that are less than 100? How can I figure out how many in that are less than or equal to 100? Once I've done that, I start a top counter here. Send my first runner down to find a green. Send my second runner down to find a blue. One of these is going to be less than or equal to 100. And the reason we have to have the difference is because I need to know this is less than or equal to 100, but not less than 100. So you can get the difference between those two. The difference between those two, or rather, if this is less than or equal to 100, but then the less than 100 on that row is 0, then that's how we know when to stop. So that's why we have less than equal to and less than. So we know to stop this one here. We know to stop that one there. And then we let our top counter work its way down until it gets past our green one. And then the green one has to work its way down again to find the next one. And then every time we count that down, every time that top pointer moves, then the difference between our blue and our green is how many potential ending points we have for a box that starts on that row. So when the top one is here, that's an ending point here, an ending point here, an ending point here, and so forth. All righty. I know it's a lot to do. This is, I would consider this one of the harder silver problems. It's definitely in the top of the hardest ones. But if you have an understanding of that general pattern, and I mentioned the lonely photo one, if I have a general understanding that I have a target here with some number of things before it and some number of things after it, and I realize I want to be able to count that, but I want to be able to count it without counting all the subsets, then for this one, I've got potential stoppers is 1, 2, 3, and 4. So I can just add 4 all at once. And every time I advance this counter, I add 4 until I hit this one. Once I hit that one, I send my next runner out to find the next central point, which in this case makes the 100s. And then I have to find the next one after that. And then again, whatever the difference between those two is, I can add that for each one of these as well. So you've got your prefix sums, you've got your nested loop picking a starting and ending column. For every possible starting and ending column, you work your way down using prefix sums to see whether there are 100s or whether they're not. You're going to have 3 pointers working your way down, 2 runners, one looking for your green row, for your row that has a 100 in it, but nothing less than 100, and one looking for your row where you have something that's like the bottom, and the bottom will either be the bottom of the grid or anything that is less than 100, but not including 100. Once you have that, you just work your top counter down. Every time you work your top counter down, you add the difference between the very bottom and wherever you found your 100 until you hit that 100, at which point you have to send that runner to find the next screen, the next thing with 100 in it, and then just keep counting the top counter down. Alrighty, good luck coding it, and I will talk to you in the next one.